how information is transmitted from one point to other point. Now suppose you are in your classroom and you want to talk to your parent without using any mobile phone or any electronic device. You want to talk to your parent. Your parents are in home. What you will do, you will start shouting at the peak of your voice. So once you start shouting at the peak of your voice, you will expect that it will reach the parents. But if they are at a far distance, it will not reach them. Why? The reason is our audio signals are of low frequency, 20 Hz to 20 kilohertz is the bandwidth of audio signals. So that cannot travel to a large distance with low frequency, energy content is low, we'll see those things. So it cannot travel to a lowest distance. So you require some method of sending the voice to a large distance. So we cannot deal it with low frequency, we have to go to high frequency. Somehow you have to have a high frequency. Similar example, similarity, you can say you want to go to Delhi. And if you keep on walking to going to Delhi, it will take long time. Not only long time, it will exhaust you. So you may not reach Delhi at all by walking. So what you do is you take a train or take a flight or take any communication. So what you are doing in that case, actually what is being done? You are the entity who is to be transferred from Berhampur to Delhi. But Berhampur to Delhi you cannot go. From Berhampur to Delhi, what is going is a communication uh, means like aeroplane or maybe like aeroplane or train. So you, the entity which is to be transformed from Berhampur to Delhi, will be taken from Berhampur, put on the train or put on the aeroplane. So you will be put on the aeroplane, then the aeroplane will go to Delhi, then you will be taken away from the aeroplane or you will be taken away from the bus or the train. So you reach the so destination you reach. So from transmission you reach the destination. This is the process that we follow nowadays with advent of technology. We follow this. So in this case, in all these cases, we have a original signal or original entity. When you are traveling, you are the original entity. If your signal, your voice is going to your parents, that voice is the original entity. So that is the base. You are the base or your voice is the base. So if you convert that into a signal, that's all signals will have a fixed band. They will be prominent over a band and beyond the band means over a band of frequency. So beyond that band of frequency, it will not be that prominent. So the beyond that band of frequency, the energy or power of the signal will be low, negligible. So the power or energy that we just discussed, spectral density, so that will be prominent over a band. So your signal is prominent over a band, which is the base signal. So that is called a baseband signal. Uh, Now let us start with baseband signal and we'll go to the introduction of modulation. So what is the definition of baseband signal? The baseband signal represents original information in unmodulated form. So there has been no change to the baseband signal or no change to any other signal. The baseband signal carries data directly without any modulation. There is the data or information is exactly in the baseband signal only. Typically, the baseband signal will have low frequency. Hello. Hello. କୁହ ଶୁଭୁନି କି ଭଏସ୍ ଯାଉନି ଆମେ ଉଠେଇନି ହ୍ୟାଲୋ ଆମେ ଉଠେଇନି ନା ସେଟା ମୋର ଅମିତ Oh, I was not on mute. So now it is. Now it is. Am I audible now?
Yes, sir. Yes,
Okay.
sir.
Okay. So set a power starting presentation mode. So I was saying that we were going to discuss about modulation, introduction to the modulation. For the modulation, I said that suppose you want to go to Delhi from here, or you want to go to Bhubaneswar. For that effect, you want to go to Bhubaneswar from this place. So how you will go? You will take a train or you will take a bus. So bus will carry you from Berhampur. You are the original entity. You will be put into the bus. So the look of the bus will change because you are inside the bus. Bus will look differently. Without you, bus will look differently. So you are put into the bus. So inside the bus looks different. Once you are put in the bus, bus goes to Bhubaneswar, and Bhubaneswar you are taken out of the bus. So you reach Bhubaneswar. So Bhubaneswar your people receive. So you are transmitted from Parampur to the bus and you are received at Bhubaneswar from the bus. And now you are the original entity. Similarly, if we transform this into signal, our voice signal or most of the signals which contain information, they are of low frequency signal. So they cannot travel to a large distance. You require some other method. So they are to be put in something like a box. So something has to carry those signals. There has to be a carrier. Your original signal is of low frequency. It exists over a band, small band. That band over which the energy content or power content is low. So that band is called the band of the signal, and this band is called the baseband signal. Why base? Because this is the basic signal, or the base signal is your original signal which contains information and which is to be transmitted. So now let us define what is baseband signal. Next. And so definition of baseband signal is it represents the original information in unmodulated form. It carries the data directly without modulation. So there is no modulation, no change is done to the data. Data is directly carried by the baseband signal. Typically, baseband signals or information content are at the low frequency. So it will have a low frequency range typically. Next. This is an example of a analog baseband audio signal. So what we are seeing here is at different audio signal. Let us look at it in the time domain. So at different times we will take the samples of the signal, which means at different time points. So say time t is equal to 0. What is the amplitude of the signal? Let us take the amplitude to be 0. At time t is equal to 0.125, the amplitude is 15. 0.25 amplitude is minus 10. 0.375 amplitude is 30. So this way we have taken the amplitude. So here we have taken samples of the signal at different times, and the amplitude samples means amplitude samples of the amplitude of the signal we have measured or found out what are the amplitudes. So this is example of a signal which is uh, sampled at 8 kilohertz. The voice is sampled at 8 kilohertz, and you can see there are 8 samples we have taken. So we say next, each sample is quantized to 8 bits. So we have taken 8 samples. You can see 0 to 0.875. These are 8 samples are there. So each is quantized to 8 bits. Now, what is the purpose of the baseband signal? This directly carries the original information. There is no modulation in the baseband signal, low frequency representation of data. This is given as input to the modulation technique that we will use. Modulation technique is used for transmission over communication channel. These are prepared for long distance transmission using modulation techniques. Next. Then let us consider it for long distance transmission. So we'll consider a baseband audio signal which is sampled at 1 kilohertz. 1 kilohertz means 1000 samples per second. Sampled means you are taking samples. How many samples you are taking? 1000 samples you are taking. That is why 1 kilohertz. Now 1000 samples in 1 second. You are taking in 1 second 1000 samples. So how in that second we are considering this. Zero time is 0.001. Since in 1 second, so 0.001, 0.002 up to 0.007. Eight labels, so 0 to 0.007. And what are the amplitudes we are seeing on the right side? 0, 50, minus 30, 20, 0, 10, minus 5, 40. These are the values of amplitude of the signal at the sample points. Next. So this represents the amplitudes of the audio signal. Next. Now, why it is unsuitable? This baseband is unsuitable signal when you are considering long distance transmission. Why it is unsuitable? I just gave you a general example. Now, what happens actually? Let us consider. The signal will attenuate as it is getting transmitted. Either you use wireless transmission or a wired transmission. Signal gets attenuated. Attenuated means the signal strength decreases as the distance increases. With distance, signal strength decreases. Now, baseband signal have limited energy content. That is another problem. So, since it has limited energy content, if it will attenuate, then it will be since it is it will decrease. The strength will decrease very rapidly. So this is particularly significant over long distance. If you have to travel a long distance, it will attenuate and you will not receive anything which is useful. So this makes the received signal very weak. It cannot be useful because of signal attenuation. Next. Then there can be interference and noise interference also. So baseband signals at low frequency, these are vulnerable to interference and noise. Why? They can corrupt these signals. Where noise and interference can corrupt the signals, and low frequency signals are of low energy. Therefore, noise and interference at these frequencies, if they are of high energy, they will corrupt it. Then, if you have long distance transmission, they will expose these signals to different types of noise and unwanted signals. This results in distortion of the signal because additional frequency component will be introduced, or frequency components, the amplitudes of the frequency components will change, resulting in distortion, and because of that, there will be reduced signal to noise ratio. So signal quality will be reduced. Second is bandwidth limitation. The baseband signal occupies a significant portion of the transmission bandwidth. Why it is occupies a significant portion of the transmission bandwidth? The reason is it is of low frequency. So since it is of low frequency, suppose you are working at 10 kilohertz. 10 kilohertz, you take its 10%, 0.1. So that will be zero point 0.1 kilohertz. It will sorry, you are working at 10 kilohertz, so you are occupying 10 kilohertz of bandwidth out of 20 kilohertz of bandwidth. Audio is 20 kilohertz, so out of 20 kilohertz, 50% bandwidth you have occupied. So it occupies a significant portion of the bandwidth. In long distance transmission, they require transmission of multiple signals simultaneously. Why? Because many people will talk simultaneously, not one person. So since many people will talk simultaneously and each one is occupying the same portion of bandwidth, ultimately it becomes like a noise. Like in your class when all of you are talking, so then somebody comes from outside, he cannot distinguish who is saying what. So that becomes a problem, long distance transmission, because of this. Then next is there is scarcity of bandwidth. So since bandwidth is fixed for audio transmission, bandwidth is fixed 0 to 2 to 20 kilohertz. So you can have only limited number of signals to be transmitted simultaneously. Concurrently means simultaneously because of the bandwidth constraint. Then there is called path loss. We have seen path loss in antennas. So this is same here, signal loss. So these signals, they experience significant signal loss during the transmission. This is caused why during transmission this loss is there because of attenuation that we have seen. Then dispersion. Dispersion means energy is distributed. Energy, original energy is suppose at frequency f. Now, because of dispersion, some amount of energy will go to F1, some will go to F2, some will go to F3. So F, the frequency content in F will be reduced. So there will be loss in signal. So distortion will lead to signal spreading to different frequencies and distortion. Distortion why? Because other frequencies will come out, so signal shape will change. Then attenuation causes a decrease in signal strength with the distance. So signal loss can make it challenging to accurately cover the original information at receiver's end. Next. Then we'll come to why we require a carrier signal. What is a carrier signal? So with baseband signal, we cannot transmit to a large distance. We require a carrier to carry the baseband signal. So a carrier signal is a high frequency waveform or a high frequency signal which serves as a vehicle for transmitting the signal or transmitting the information. This is an unmodulated signal in its pure form. This is unmodulated signal. The vehicle, when you have not entered the vehicle is unmodulated. So when you have not put the baseband signal on the carrier signal is unmodulated, so it does not contain any information on it. Instead, it carries the modulated signal or modulated information from the baseband signal. Once baseband is imposed on it, it will carry the information. So the carrier signal's frequency is typically much higher the baseband signal's frequency. So it is essential for long distance transmission because it efficiently propagates with less attenuation, less noise, less loss. It propagates efficiently through the communication channel. It acts as a medium to carry the multiple signals. You can put multiple signals on the carrier signal. So many signals can be transmitted through the carrier signal using different frequencies for each channel. This is used for as a modulation technique to combine baseband signal with it. So each carrier signal will have different frequency. Modulation results in carrier signals change in carrier signals amplitude, frequency, or pitch. The modulated carrier signal is transmitted over the communication channel, which is delivered on the encoded region. So now let us consider the energy content of baseband and carrier signal. Compare them. Why baseband signal cannot be transmitted? Why carrier signal can be transmitted? What is the energy content? Why the baseband signal attenuates fast compared to carrier signal? Next. So let us see a baseband signal. So we'll sample it at 1 kilohertz. So 1000 samples per signal. Each sample will have an amplitude value representing the audio signal's intensity. So these are the amplitude values. Take a snapshot of this table. So 0, 0.5, 0.2, 0.3, 0, 0.1, 0.1, minus 0.1, 0.4. And what is the time? 0.001. That is the time difference. So 0.001. So in that we go up to 0.007. So 8 samples we have taken next for the best one. Now for the carrier signal, we have a 1 megahertz carrier signal. So much higher than, so that was 1 kilohertz, this is 1 megahertz. So 1 million cycles per second. So here what will happen? So time 0, then next time will be 1 e to the power minus 6, 1 into 10 to the power minus 6, 2 into 10 to the power minus 6 up to 7 into 10 to the power minus 6. Now what will be the carrier signal? Sine, let us consider the sinusoidal signal. So it will be sine 2 pi f. F is 1 megahertz, which is 1 e0, 1 e 6. Then 0, and that will be multiplied. So at 0 it is 0. Then 2 pi ft. So t is 0 for the first one. For the second one, t is 1 e to the power minus 6. Similarly, for the last one, it is 7 e to the power minus 6. So this is the carrier amplitude. Now, if you compare these two, to compare the energy content of the baseband signal with carrier signal, what we will do is we will calculate total energy for each signal. How will you do that? By summing the squares of their amplitude. Now for the baseband signal, the total energy will be this much: zero point 0.5 square plus zero point 0.2 square of this series. So then for the carrier signal, they will be sine 2 pi 1 e to the power 6 into 0 square. So this way, all the component amplitude component square. Now if you compare these two, calculate these values and compare them, then total energy calculated from both the signals, baseband and carrier, that will show you, do the calculation and see that the carrier signal exhibits significantly high energy content compared to the baseband signal. So carrier signal operates at a much higher frequency than the baseband signal. That is why it carries higher frequency. So higher frequency leads to higher amplitudes. Higher amplitudes leads to total more energy. So more energy is carried by the carrier signal and due to its high amplitude and frequency. Now let us consider what is modulation next. So based on this, once we are equipped with what is baseband signal, what is carrier signal, what are disadvantages of baseband signal, what are carrier signal, and why there are advantages that we have considered. Now we come to modulation. What is definition of modulation? Modulation refers to the process of altering a carrier signal in order to encode the information or data into it. Or you can say we are altering a carrier signal in order to encode the baseband into the carrier signal. This involves combination of low frequency message signal, which is the baseband signal, with high frequency carrier signal to produce a modified signal, which is called the modulated signal. So you have a baseband signal, you have a carrier signal, and when the carrier is modified according to the baseband signal, that is called the modulated signal. So we have three signals. Why modulation is needed? Now from that definition, now let us come to what is the need of modulation, importance of modulation in electronics next. First is efficient use of transmission medium. So modulation allows transmission of information over long distances. Second is multiplexing. Modulation enables multiple signals to be transmitted simultaneously over the same communication channel. So efficient use of resources. Then compatibility. Modulation ensures that various electronic devices can communicate with each other by using standardized modulation schemes. Noise immunity. Some modulation, not all, some modulation techniques can enhance the resistance of the transmitted signal to noise. So overall integrity is increased. Next. Now, bandwidth utilization, as I have told now, so modulating signal to higher frequency. Suppose you are using 100 hertz and 10 hertz and 100 hertz. So lower frequency is 10 hertz. Its 10% is 1. Bandwidth will be 10 hertz. Bandwidth will be 1. So 100 hertz, 10% will be 10. So same 10%, but at 100 hertz you have 10 bandwidth. So 10 times the bandwidth. So that is how bandwidth increases as you go to the higher frequency. Next. The security of the signal modulation, they can be used to encrypt and secure information transmission during the transmission. Uh, the most important part is the size of the antenna. Now let us consider a scenario. Suppose we want to transmit an audio signal, which is the baseband signal, and you want to transmit the baseband signal over a long distance using a radio communication system or an antenna. Now, baseband signal, in this case, in this example, let us consider an audio waveform sampled at 10 kilohertz, which means 10,000 samples per second. 10 kilohertz, we are sampling it. So, accordingly, time will be 0, 0.0001 up to 0.0007. 8 signal samples. Values are given here: 0, 0.5, zero point 0.2, minus 0.30, 0.1, minus 0.14. These are the baseband amplitudes. Next. So this is the baseband signal. Now consider antenna size. I will assume that we are sending this baseband signal directly for transmission without modulation. Now that will lead to the baseband signals frequency range will be limited to 5 kilohertz, highest frequency component and lowest frequency component difference is 5 kilohertz here. To achieve transmission, efficient transmission over a long distance, the antenna size that must be proportional to the wavelength of the signal which is being transmitted. Now wavelength lambda is inversely proportional to the frequency and it is given as lambda is equal to c by f. Now c is speed of light 3 into 10 power 8. Okay, so now find out what is wavelength. Next. So find out the wavelength. Wavelength will be next. Highest frequency component is 5 kilohertz. So wavelength lambda will be c by f. So 3 into 10 power 8 by 5 into 10 power 3. Right. So that gives you 60,000 meters. So wavelength is 60,000 meters. So antenna length will be about 60,000 meters, which means 60 kilometer length of antenna. That is not practical. Next. So such antenna is not practical. For efficient transmission requires an antenna for matching the signal's wavelength, which is 60,000 or 60 kilometer. That is not practical in this case. Next. So you cannot put such an antenna anywhere. Forget your portable devices like laptop or phone. 60 kilometer antenna you cannot put in your phone or laptop, so it is not possible. Therefore, baseband signals cannot be transmitted wirelessly. Wireless transmission of signal is not possible. Antenna size becomes very high, extremely high, impractical. Next. Next. So when you do modulation, what you do, you use a carrier frequency. Once you use a carrier frequency, and carrier frequency is modulated at the baseband, carrier frequency range is very high. So high carrier frequency will have short wavelength. Short wavelength means antenna size is small. So practical antenna size is possible when you use modulation. Now, there are two types of modulation. We consider first the linear modulation. Different types of modulation we consider the linear modulation. So, let us have an overview of linear modulation. Linear modulation technique, they maintain a linear relationship between the input signal and the output signal during modulation. So input is your baseband, output is your modulated signal. So between input and output, baseband and modulated or original signal and the modulated signal, there is a linear relationship. So these techniques are widely used, particularly in communication system, analog communication system, where amplitude, frequency, or phase of the carrier is linearly varied with the message signal or baseband signal. Baseband signal is called original signal or message signal. So linear modulation includes three primary types: amplitude modulation, phase modulation, and frequency modulation. Next. In amplitude modulation, the amplitude of the signal of the carrier signal varies in proportion to the amplitude of the message signal. This will result in DSB double sideband or single sideband signal or amplitude modulated signal. Next. Next. In frequency modulation, carrier signal changes, the frequency of the carrier signal changes based on the instantaneous amplitude of the message signal or the baseband signal. This produces a frequency shifted signal. In phase modulation, phase of the carrier signal varies in response to the message signal, which leads to phase shift in the signal generation. Linear modulation is commonly used in broadcasting, means radio stations, telecommunications in telephones, radar, and other analog communication applications. Now, we will consider different types of modulation. Next. We have just seen there are three types. One is amplitude. The principal amplitude is amplitude of the carrier of the signal will vary in proportion to the instantaneous amplitude of the baseband or message signal. So carrier amplitude will in the modulated signal, carrier amplitude varies proportional to the instantaneous amplitude. Remember this instantaneous amplitude of the baseband signal. Instantaneous is important. The baseband signal contains the information to be transmitted, while carrier signal provides the means to carry the information or transmit it over long distance. Next. AM waveform and spectrum. So AM waveform consists of a carrier signal with varying amplitude as per modulating baseband signal. AM spectrum consists of carrier frequency and two sidebands located symmetrically around the carrier frequency. Pictorially, we will see this when we will come to amplitude modulation, details of amplitude modulation. The sidebands in the AM spectrum, they contain the modulating signals information and they carry duplicates of the baseband signals frequency component. So carry signal information and carry duplicates. Next. Advantages are simple to implement and demodulate, efficient use of power for transmission, suitable for broadcasting audio signals. Disadvantage is susceptible to noise and interference, uh, inefficient use of bandwidth compared to other say modulations, limited ability to handle multiple signals simultaneously. Then we'll come to frequency modulation. FM modulation technique. Here, frequency of the carrier signal varies in proportional to instantaneous amplitude of the baseband signal. I have left the instantaneous, so you put them. Instantaneous amplitude of the baseband signal. The baseband signal's variations cause the frequency to deviate above and below its center frequency. Center frequency means the original frequency of the carrier wave. So that is the center frequency. It can increase or it can decrease according to the amplitude of the baseband signal. Next. The FM waveform that exhibits varying frequency deviations based on the modulating baseband signal. So the spectrum comprises of carrier frequency and an infinite here. There will be an infinite number of sidebands. In the amplitude modulation, there are two sidebands here, infinite number of sidebands, spaced at multiples of the modulation frequency. Advantages are high noise immunity resulting in improved signal quality, efficient use of bandwidth, making it suitable for high fidelity audio transmission. That is why audio FM radio is very famous. Ability to transmit multiple FM signals within the same frequency range that in our advantage. Disadvantages more complex modulation and demodulation circuit compared to AM, and it requires more power for transmission and it has limited coverage. So range is limited. Next. Then phase modulation. The principle is the phase of the carrier signal varies in response to the changes in the baseband signal's amplitude. The variation in phase corresponds to instantaneous amplitude. Uh, Instantaneous amplitude of the modulating or baseband signal. Just a minute. Give me 2 minutes. Uh, change. The phase modulated waveform that will change in carrier signals phase if there is any change in carrier signals phase which is proportional to modulating signal, then that will change, waveform will change. The spectrum consists of carrier frequency with sidebands similar to FM but with a phase modulation index which determines the sideband amplitude. What is the sideband amplitude? That is determined by this. You don't require PM modulation, phase modulation we don't require now. Digital communication will require it. Next. 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 Advantages are the first advantage is next less susceptible to noise compared to amplitude modulation. So you have signal integrity. Next, efficient use of bandwidth. Next, widely used in digital communication systems, uh, using PSK phase shift key modulation. Next, disadvantages are these are more complex to implement and demodulate complex circuits, less common in traditional analog broadcasting due to complexity of the circuit, limited commercial applications. Compared to AM and FM, the commercial application is minimal. Now let us consider the advantages of the carrier signal, its importance of the carrier signal. We'll see one numerical example to understand what is this. So this example is we are considering a carrier signal next at 1 kilohertz, which is sampled audio signal, which is sampled at 1 kilohertz. So 10,000 samples per signal. Each sample of the baseband signal will have an amplitude which represents the audio signal's intensity. So this is as in the other cases here is also same. And this time is 0.001 difference 7 distances 7 samples. Next. Now carrier signal is 1 megahertz or 1 million cycles per second, and again it is simple sinusoidal wave. You can see it is sine 2 pi 1 into e to the power 6. 1 into e to the power 6 is frequency 1 megahertz. That into time 0 or 1 into e to the power minus 6 is time, 2 into e to the power minus 6 is time, 7 into e to the power minus 6 is time t. Next. So those are the so why carrier signal is important in communication system based on that. First is frequency translation. The carrier signal is important because it allows frequency translation of the baseband signal. So baseband signal from low frequency you go to high frequency. Based on the carrier signal, you translate the baseband signal to a high frequency for transmission. So that is one for long distance transmission. Next, efficient transmission by modulating the baseband signal with carrier signal, we shift the frequency to baseband signal for higher frequency, so we can transmit efficiently over a long distance. Next. So, as I told you, long distance communication it is possible with only carrier signal. Next. Channel allocation. So using carrier signals for different frequencies, different carrier signals of different frequencies, so you can have multiple channels can be allocated for different types of communication purposes. Next. Demodulation at receiver is possible with is easy. You don't require demodulation in baseband, but if you have carrier circuits, demodulation circuits are easier. Simple circuits you can use for demodulation at the receiver, and you can recover the original baseband signal there. Next. Now let us consider another numerical example of modulated signal and its deviation. As I told you, it deviates from the carrier signal deviates. So this is the baseband signal. It is at 1 kilohertz. Sampling is 1 kilohertz audio signal sampled at 1 kilohertz or 10,000 samples. So this is the same one that we have seen earlier. Next. Then this is the carrier signal which is being modulated or changed. The signal is by the baseband signal. Sampling is at 1 megahertz or 1 million cycles per second. Uh, the time is given 0, then in steps of 1 into e to the power minus 6. So 1 megahertz, so 1 into e to the power minus 6 time we are taking. Carrier signal will be sine 2 pi, then frequency is 1 into e to the power minus 6, then time will be 1 into e to the power minus 6, 2 into e to the power minus 6, up to 7 into e to the power minus 6. Next. So these two are given. Now we will derive the modulated signal for AM. So let us try to derive from these two baseband signal and the carrier signal. Let us try to derive the modulated signal based on this. Next. So modulated signal, you can see the time remains same 1 e to the power minus 6 up to 7 e to the power minus 6. So time instances where the samples were taken of the carrier, those are remaining same. Now the amplitude of the modulated signal will be different from the carrier signal. The first part, the sine part, remains same as the carrier amplitude. So sine 2 pi 1 e0 c 1 E6 or 10 to the power 6 into 0, 10 to the power 6 into 1, 1 into 10 to the power minus 6, so up to 10 to the power minus 7 into 10 to the power minus 6, those remain constant. Then with that sign component is multiplied the amplitude component of the baseband signal, which is 0, 0.5, 0.2, corresponding to those sample values. Those are the amplitudes of the modulating signal or the baseband signal. So this gives you the modulated signal amplitudes. So right hand side, this is how the modulated signal amplitude is obtained. Next. So I gave you the explanation, so I'll skip this. Next. Okay. The baseband signals amplitude changes, these are imposed on the carrier signals that we have seen. So this resulted in modulated signal. The modulated signal carries the information present in the baseband signal for transmission that we also have seen from the example. Now the carrier signal frequency 1 megahertz or 1 million cycles per second. Similarly, the next. Carrier signal retains its frequency, it has not changed. 1 megahertz or 1 million cycles per second, that has not changed throughout the modulation process. What has changed is the amplitude of the carrier signal. That has varied with the baseband signal's amplitude. Modulated signal has a constant carrier frequency. The carrier frequency, constant carrier frequency. So modulated signal frequency is same as the carrier signal's frequency. That is 1 megahertz. Amplitude variations in the modulated signal, they correspond to the original audio waveform in the baseband signal. That is what has happened. Next. So with that, we come to the end of our introduction to this modulation. Next class we'll start amplitude modulation, and we today what we discussed, two things we discussed. One is spectral density, under which we consider two types of spectral density: amplitude spectral density and power spectral density. But